Our first speaker is Antonio Loquercio. He received the ETH medal for his outstanding master thesis in 2017 and is now working on his PhD in the Robotics and Perception Group at the University of Zurich. And he focuses on data-driven methods for perception and control in robotics. And today he will talk about learn vision-based agile drone flight.
Thank you very much for the introduction, and welcome everybody to my talk. What we will speak about today is learning vision-based agile flight. Before I start, that's a link to my website. I'm going to upload the slides afterwards in there, if you're interested. So before going into robotics, a few words about my group. We are the Robotics and Perception Group, kind of 20-25 people, like 15 PhD students, 5 senior scientists, and the rest kind of visiting. We are both in ETH and University of Zurich, and we're funding a bit from everywhere. Our vision is creating this kind of drones. So small drones that can fly fast and autonomously with only onboard sensing and computing in uncontrolled environments, like a museum, a house, a supermarket, and can do several tasks, like communicate between each other, go out, go in, depending on their mission, and exactly what you see here. The problem is, this is still very far from being reality. What you see here are just computer-generated drones, the majority of them. This is just an advertisement of a car. There are still, this is our vision, but there are still many problems, both technical and fundamental, that have to be solved before getting there. Robotics indeed gives us a lot of challenges, in particular mobile robotics. First of all, perception is very difficult, in particular when you have low texture, HDR scenes, and motion blur that are induced, for example, by fast motion. And also many algorithms developed for control of mobile robots. They're mature, they've been there for a lot of time, but they are actually not robust. If you put them in an uncontrolled environment, I don't know, in a city, in a house, you will see its performance to decrease quite significantly with respect to the lab-controlled conditions. Another problem that we see is that control and perception have been considered mostly separately by roboticists for the last years. And that's a problem, because we know they are the way we see and the way we act is highly correlated. And keeping this distinction for robots is just hindering further performance. Also something that we start seeing in the field, but is still not yet there, is having robots learn from their experience, because we don't want them to make again and again the same mistakes. So, of course, the question is, shall we directly go straight to reinforcement learning for navigating a drone? Well, in the end, every problem can be modeled as a Markov decision problem, so yeah, easy, right? Just say, okay, my task is going from A to B, my reward is getting to B as close as possible, and that's it. Actually, there are some problems. First of all, for doing this kind of things, you need plenty of robot experience. And this kind of experience is very expensive from a robot point of view. Not only in terms of the batteries, of the motors you're going to use, but also because doing trial and error with an unstable platform like a drone is quite dangerous. How many people here have ever flown a drone? Okay, so some, and I guess you know that it's not easy to hover, to just stay in place. If you make a single mistake, your platform is gonna crash. So that's why robots, real-world reinforcement learning with drones is kind of complicated. It's not that difficult to get these kind of broken platforms. And so one solution could be, okay, let's go to simulators, do everything there. But the problem is that simulators, they poorly model aerodynamic effects, or at least high orders of aerodynamic effects. Here I'm speaking of real-time simulators. Of course, there are some super expensive simulators that model everything, but that's kind of not the kind of things we want to use. And that's kind of very limiting for learning with a platform that moves and lives because of aerodynamics. So I'm gonna explain in this talk a bit what we are doing in this direction, what we're doing to reach our vision. And I will present basically divided in two chapters. First, I'm going to speak about deep drone racing, and then I'm going to speak about a novel sensor that I think has really a lot of promises for mobile robotics, and we're going to see more and more in the next few years. So let's start with deep drone racing. How many people know what is it? 1, 2, 3, not that many. That's what drone racing is. There are pilots, professional pilots that control drones at very high speed in a truck. It's like Formula 1 but for drones. So there is a camera mounted on top of the drone, and the pilot tries to compete against other pilots. The goal is finishing in as fast as possible. See, this is very complicated. The environment is full of occlusions, the motion is very fast, there is motion blur everywhere, there are high dynamic scenes like light, dark. Having a real robot doing this is impossible, at least for now. So drone racing, it's very cool, because it raises fundamental problem of robotic research. In particular, it raises the problem of doing real-time coupling of perception and action. Things change so fast that you cannot just first perceive and then act. You have to do them at the same time. And also, since you have to go that fast, it pushes you to cope with all the inaccuracy in the models that you have, of the platform itself, of the sensors, of the actuators, but also of the environment. Because in such kind of tracks, usually the environment is not fixed, it's not static, things change, people walk through the track, some gates are moved. And current robotic algorithms for navigation, they are very challenged for this. And also, the problem is coping with unreliable perception, that is due, again, by motion blur, low texture, or HDR scenes. Of course, we don't do drone racing just because it's cool. Our goal is to beat the best human pilot, but we don't want to do that just for fun. We think that drone racing, the knowledge we acquire in drone racing can be transferred in a lot of applications, like, for example, delivery, surveillance, or most importantly, search and rescue. So, we already started tackling this problem a couple of years ago. I'm going to present you a bit what we did and what we are doing, what we're going to do in the future to continue to improve. That's the first project that did this, and it's indeed called deep drone racing. So, I'm going to explain a bit how it works. What you see here is a model of our platform. It has a front-facing camera in the front that captures images approximately at 30 Hz. Motors on the other side of the spectrum have to be controlled at 1 kHz, so kind of significantly faster. So the question is how to pass from camera images to motor commands. Doing directly this kind of inference is complicated, if not impossible. So we decided to take a modularity approach. The motor commands are produced by a hierarchy of controllers. Low-level one, where they actually produce the motor commands, and high-level ones that produce instead thrust and body rates for the platforms. These controllers are fed by a trajectory generation module that just produces the input that the controller needs. I like to call this part the muscle of the drone. Basically, this part is responsible for taking the drone wherever you want. It's like our muscular system. And the cool thing about this part is that you have to code it and tune it a single time for a platform. You don't have to do that several times. All the calibration needed by the controller and all the dynamics, they have to be calibrated only once. the brain of our system is a neural network that is fed with camera images and produces the waypoint and speed where the drone wants to go. So basically we separated the problem. There is the neural network that is telling where to go and how fast to get there, and the muscular system, so the controllers, they're going to actually take you there. So that's a bit, again, how the approach works. Take the image, pass it through a neural network, you produce three outputs, a point in image coordinate, x, y, and a speed how to get there. You project this point in 3D, and then you produce a trajectory from where you are to this point. And this trajectory is then tracked through like this controller scheme. How to train this network? So how to teach a network to select places where to go in a racetrack? The approach we used was imitation learning. So indeed it is sample efficient, doesn't need to break drone during a racetrack, that's also nice. And also it's easy to find experts that could solve these tasks if you give them privileged information. Unfortunately, I can't go in more details for that, but you can look at the reference or speak with me later if you want to know more. What I would like to show is the system in action. So that's the drone, like in a racetrack we built just down here, and is kind of navigating autonomously with just onboard sensing and computing. Like everything is run on the little computer on top of the drone, both the neural network and the controller. What you see here, it is robust against drift in state estimation that are usually induced by, for example, motion blur or low textures or classical problems of perception. So this approach works quite well, and it can do several laps, actually as many as you want, without drifting. Of course, you might wonder what is like the performance of this approach with respect to human pilots, to the first video I show you, just at the beginning. I'm going to show you this in this kind of plot, where you basically see in two axes the success rate against the average lap time. Usually you want to be in this part of the graph, in the green part, where you have like high success rate, so you never crash, but you are also fast, so average lap time as small as possible. We are now in here, so we have a lap time that is okay, but like we are very repeatable, like we can close the track 100%, never fail. If you take a classic robotic algorithm that basically is just state estimation plus the control on top of that, you would have a very low performance. And this is due, again, by all the problems that perception has. So motion blur, low textures, and similar. An intermediate pilot, so a person who knows how to hover, that knows how to fly, but is not very good, is around this part of the graph. So it's kind of a bit faster than ours, but like it doesn't have a lot of success. It crashes very frequently. While if you take a professional pilot, that's a pilot who flew in the like Swiss competition, the drone racing Swiss competition, you have it a bit down here. So like it's almost perfect in terms of success rate, but very fast. So our system is good, but still our goal in the future is to push a bit down.
Can I ask one question?
Yes,
When
please.
you use imitation learning, are you using data from these professional pilots or amateur pilots?
We could use that, but actually we use data from an algorithm expert that has access to privileged information. That is the global state of the platform. So it would be also possible to use them. We are taking into account just the problem that every time you need to recollect data, you have to pay a pilot. So what I wanted to show you in here is that our approach, so sorry for, yes, like we both were kind of, me and our colleague, we had our face covered because this omission was double blind, so we couldn't show our face. And basically what I want to show you here is that the network is not just memorizing, copy-pasting the action that it received at training time. It's actually adapting to the environment dynamically. Whenever it, let me play it again. It's blocked, I don't know why. But whenever the the track changes, the network will adapt accordingly and go in the center of the next gate. But we also said it before, data generation is done with an expert and actually it's kind of a laborious process and pretty error prone. For every new track that you want to fly, you need to go there and label the track in a kind of precise way. You need clean data if you want a good network. And the problem is also you have to repeat it for every new environment. So, of course, the idea was, can we train this policy in simulation and then just apply it as is to the drone? The answer, of course, is yes. And the way of doing that is using domain randomization. I don't know if you're already familiar with it. It's basically the concept of going in simulation and randomize everything you want to be invariant to. And for our case was the illumination of the environment, the appearance of the gate, so a bit circular, a bit core kind of with more hedges, and also of course randomize the background and the floor because we want it to work in the same environment. That's a bit an extract of how our training data looks like. So you can see there is a bit of everything, like different illumination, different gates, and different background and floors. We trained this policy exactly in the same way. Now the expert is only presented in simulation. And then we took this policy and applied it as is to the real platform, without any changes. We tested then, again, in the same track as we did before, but challenging our drone to cope against difficult conditions, with harder and harder illumination, where there was almost no light, and also having distractors around. So some people that would walk in front and cover part of the gate. As you can see, the system worked quite well. With an easy illumination, it was absolutely perfect. It could complete the track with 100% success rate. Also with medium illumination, that's basically two lights in the center of the room. You can basically see them here. The system was quite robust, but probably my favorite one is the one that is now coming, that is with basically a single light source. You can see everything is dark. That is what the drone sees, almost nothing. And still, in this difficult condition, our policy training simulation is able to control the drone pretty well. Also, the policy is robust against distractors. Distractor is now me dancing in front of the drone. You can see that it's basically not affected at all by it, and it's just because we had some distractor also in the simulation. So, of course, you might wonder if this representation that we found, which means having a network that produces only waypoints and then leave the motor, so the muscle, to the real platform, would also generalize not only sim to real, but also allow to use reinforcement learning. The answer is again yes. This is an ongoing work, so I don't have cool videos to show. What I can tell you is that we are using a very similar approach but now our network not only produces the three output of before, so the point and the velocity, but also a Q value, basically the classical Q function used in reinforcement learning, and with the deep deterministic policy gradient, an agent that starts with a suboptimal policy is able to improve its policy more and more in time. The reward we use is very intuitive. That's instantaneous reward, and it just tries to minimize the distance to the next gate, a time penalty. Of course, we want to be as fast as possible, and also we have a collision penalty. So if we go like crashing against the gate or the floor. That's some preliminary result. You can see this is the policy of initialization. It was trained in simulation for a track that was a bit different, that had basically this shape. And of course, when replaying it, the approach is not perfect. If you then run DDPG, like if you see it also, you will see here that is the optimal policy, the circular one. You can see that like the reinforcement learning algorithm converges to the optimal policy after approximately 1,000, 2,000 steps. So pretty quickly. We are working on it. Stay tuned for more results. And that's about it for what I wanted to speak about drone racing. It's very cool, it's a very, very interesting problem, and we are looking forward to get more results in the future and beat the best human pilots. Doing that, of course, like raises more challenges that are also technical. I think that frame-based cameras, they are not enough. For going more, we need a super eye, and that's what is for me the event camera. What you see here is basically a video of very fast sparrowhawk like hunting, and you see that like this is like it not only goes very fast, but it passes through constrained environments like in a speed that is impossible for autonomous drones. That's impossible not only because if you go that fast, your perception system will automatically break, but also because this changing shape, this passing through constrained environment is just not compatible with the current perception algorithm. So like we start asking ourselves, what do these biological agents have that we don't? Many things, but one thing for sure is that they don't have a frame-based cameras. They don't collect frames at 30 Hz. And that's something that people working in computer vision, I think, know very well. Computer vision is great. There's been research there for the last 60 years, and we've seen impressive things. But whenever there are agents moving in a speed that is like more than just like walking around, some effects start to appear. For example, an autonomous car that drives fast wants to minimize latency as much as possible, so, and detect, for example, an obstacle in before it's too late. And doing that, like when you're moving fast, believe me, it's quite complicated with a traditional algorithm. Then also motion blur is a problem. Like, for drones, going fast in environment with not a lot of light, you're always gonna have motion blur. And classical algorithms, they're still coping not very well with that. Dynamic range is again another of the problems that, still not quite solved. Cool thing about it is that event cameras are a completely different sensor that do not suffer from this problem and has a lot of opportunities exactly in these scenarios. So, what is an event camera? Before explaining what is it, I would like to basically quickly remind how a frame-based camera works. So basically, a frame-based camera at constant intervals, it collects a frame, so like all pixels synchronously, say 30 Hz, and then stores everything in memory. It doesn't care if something moved in the environment, if the environment is completely static. Every 30 Hz, save all the pixels together. An event camera instead is a sensor that is sensitive to motion. Whenever something moves, whenever there is a a light change induced by motion or by the changing of the light in itself, the event camera will spike. So this is the output of a standard camera, frames in time. This is the output of an event camera. An event camera is still a camera because it has pixels, but every pixel responds asynchronously in time and space. So it's completely independent, a pixel is completely independent by its neighbor in the image plane. And again, if nothing moves, event camera will not produce anything. And if motion is very fast, the standard camera will be affected by motion blur, while the event camera will capture all the details of the motion. So, the event camera is extremely low latency, no motion blur, we've seen it, and it also has a very high dynamic range. It's 140 decibel instead of the 60, and that's quite a lot. It's quite a lot. In fact, you see, for example, here a picture of somebody taking a picture of itself with a hand and the moon on the back. So it's kind of extremely has an extremely high dynamic range, and also is ultra low power. It consumes way less than a normal frame-based camera. So I've been speaking about opportunities and advantages of event cameras for the last 2 minutes. That's good. There are a lot. Problem is that traditional visual algorithms cannot be used. Indeed, event cameras again produces asynchronous spikes in space and time, and visual algorithms, they are designed for frames that arrive constantly in time, and they have all pixels there. What do we do? So, again here, another example. What you see here is a coin, falling down in front of a fan, and while a standard frame, a conventional frame, will have problem to detect the motion, will be completely affected by motion blur. Basically, what you see here, an event camera is able to capture the detail of the dynamics of both objects. So basically segment them and say what is the velocity at every instant of time, continuously. So it's kind of quite good sensor. This algorithm was, but this is not a conventional algorithm. This is something we developed in-house. You can have a look at the paper if you're interested. And again, some output of the event cameras. You see here the standard camera, and here what the event camera sees. So if we move, if you move in front of it, you will see basically only the edges of the moving objects. But of course, in case you start moving the camera, then you're now gonna start to see edges of the environment. So it's basically a camera sensitive to motion, induced either by ego motion or by motion of the objects you're looking at. Of course, I hope you were wondering, did you already use this for flying drones? The answer is yes. And we actually did something very cool, that is to let drones fly in very low light conditions. So you see here a drone that is basically asked to draw in circles in our flying room. That's our flying room, it's just down here. And at some point, the light would be switched off and on, so continuously. There is this HDR component, and thanks to the event camera that works together with the standard camera and IMU mounted on top of the drone, the drone will be very robust to this kind of situation. Of course, another very interesting question is learning with event data. That's again a bit challenging, because the input again is asynchronous in space and time. How could we use that with a neural network, for example? First, we have to convert this sparse and asynchronous input into a dense-like representation that then could be fed, for example, to a generic DNN. We solved this problem in our recent paper that we submitted to ICC, that we presented to ICCV this year, and we basically did that learning a quantization. So we take, this is the output of event camera in space, so x, y, and time. We then have a learnable quantization model that converts this asynchronous output into a synchronous representation. It's a 4D representation. Fortunately, I don't have time for the mathematical details, but that's nothing more than convolution and sampling. So both a differentiable operation, so we can maintain the full differentiability and can optimize for a task from this asynchronous input. This approach indeed achieved state-of-the-art on several tasks. For example, on object recognition using supervised learning, it beats all of the methods out there that also are there for these benchmarks. And it also works very well in the task of optical flow prediction. Again, using supervised learning. And as you can see, for example, in this scenario, there's a standard frame at night, and the predicted optical flow is extremely good. Basically matches the ground truth optical flow. Of course, one of the things we are very interested too is use event cameras for control. I showed you at the beginning this video with the bird flying very fast. I think that's the future. And reinforcement learning is going to take there. We still didn't do a lot in that direction, since the area is so new. But I think two areas will mainly benefit from it. The first one is moving obstacle avoidance. So something like this. That's something that we already solved with classical methods. So in very model-based fashion, we are now working of doing this in an unconstrained environment, basically outside, using RL. And other area that could, in my opinion, benefit a lot is high-speed control in HDR scenes. So, for example, something like this, in which you have a car that is asked to drive fast through a track at night, and it sees some HDR environments sorry for the video, for example, entering and going out of a tunnel. So I would like to conclude saying that, some takeaways of this. First of all, autonomous vision-based agile flight is still far. I think at least 10 years we are working on that. RL has a big potential for robotics, but only through intermediate representations that are robust and domain invariant. And I hope I also sent you the message that event cameras are really a Pandora box for robotics. And they have a lot of promises, in particular for high-speed motion and high dynamic range on scenes. And they will allow in the future very low latency control. So with this I conclude, and thank you very much for your attention. Yes. Yeah.
Maybe a few questions if you have.
Yes. Please.
Okay. So I'm not sure about robo racing, but for autometry and all such tasks, you're using inertial fusion systems, right?
Yes.
You always have it. So in terms of RL algorithms, is it only the vision component that uses RL algorithms, or also the IMU part of it?
No, we usually use also the IMU. We try to make use of all the inputs we have.
So
of course, that's a bit challenging because inputs come at different frequencies, but these frequencies are constant. Usually IMU comes, depends on the IMU, can come up to 1000 hertz, cameras instead they go from 30 to 50, and this is constant for operation, so we can mimic very well.
So how does the system work? Different RL systems for both the components, then something like voting, or do you combine the signals from both the components and then send it to an RL system?
I guess that's more of an implementation details. I don't know just which one would work the best of the two scenarios. I think it's task dependent. For some tasks, for example, hovering, knowing like the IMU is less important than when you go very fast, because when you hover the IMU signal is very noisy. So I guess in that scenario IMU has to be a bit far down in the loop. For other tasks maybe it has to be a bit more in front. So I don't know, it's very task dependent. Yes.
What did you use on the drone for processing?
We have an Intel Upboard. It's basically a small computer that can run Linux on top. It's like it has the same x86 architecture of a normal computer. It's very limited in performance. I don't know exactly what's the RAM and what's the compute power, but you can't expect a lot of it. Like it will completely be full with a network and an odometry system running. Yes.
What's the capacity of your model and what's the theoretical threshold or limit of the hardware that you have on it? So what's the maximum frequency that it can handle?
You mean maximum frequency of the network?
Yes.
So the network, at least when we developed this system, could run at most at 10 Hz. That was like the very limit, to leave some capacity also to the control algorithm for processing. We are now working with the NVIDIA TX2 and the new TensorFlow RT version that are making inference way faster. Yes?
You spoke about event-based cameras.
Yes.
I understand that it is to solve the latency problem.
Mm-hmm.
But RPG has a very great reputation with omnidirectional cameras right now. So can you shed some light in how omnidirectional cameras can maybe revolutionize drones in future? Something like that.
Yeah, I mean, like I think omnidirectional cameras, they are good. They allow you to see more. You have more information. You can probably do better actions, but they still have the problems of normal cameras. They are synchronous, they are affected by motion blur, and they don't have a high dynamic range. So I think maybe they could do more, in particular in obstacle avoidance tasks, but in some other tasks like racing, you just want to know where you are, like, and where you want to go. So yes.
Yeah. So you always have a 2D image and you try to represent the space in 3D. So your target is always a point, 2 dimension only, and then the speed as well. And how do you assess the distance then? And would having a second camera would help to actually make some stereoscopic vision to actually assess the distance that you travel?
Yes. So like we like the network produces a point in 2D. Yeah. That's correct, and a velocity. These are transformed into a 3D point using basically a fixed rule. Whenever the velocity is basically this distance d, it's kind of proportional to the velocity. Whenever the velocity is like low, the point is closer to the drone, and that's why usually you go on low velocity when you want to do sharp curves, and there you need to be very precise. Instead, whenever the velocity is high, like the point is far away from the drone, and that's because they will give you smooth trajectories whenever you just need to go straight and fast.
Okay, my next question would be also, how do you do when your target is outside of your camera? So when you lose so on your video, more or less always the targets are visible from the drone. What happens if you lose the target?
As the target, you mean the gate? Well, for this, the network has kind of an internal bias. So in simulation, we built also a track that is circular and is trained whenever it doesn't see anything to go right. Okay. So and that's how it's going to find the next gate. I guess you can also do more heuristic there. I don't know, put some markers or find more, I don't know, creative way, but that's how it does it. Yes.
Hasn't followed from the beginning, but can you use events from other sensors, for example sonar, radar, etc., and incorporate this to your model or to your calculation
Of course. I mean, I guess the more the inputs, the better is going to be the performance. What I'm afraid of is that the more sensor you put on the drone, the heavier will be the drone, and the more difficult will be to control it in an agile fashion. And also, what the problem you have is that more inputs require more processing, so you need bigger compute. That, of course, requires bigger processors. So, like we try, since in our lab our mission is to build agile drones that are small, we never go over like cameras or I don't know, Terra Rangers. Yes.
You mentioned Linux. Do you use a robot operating system on top or just Linux?
We use ROS, yes.
Okay, let's move on then.
Yes.
And thank our speaker again.
Thank you very much. Yeah.